Okay, so welcome to the second chapter or second video in this series. I don't know for how long it will go on, but this time I'll be covering the next two sections on Lorentz transformations and Poincare algebra. So, although Lorentz transformations are easy, but we'll just review them rather quickly, and I also have all of my notes already prepared, but I will try not to refer to them and I will try to do everything from scratch as much as possible. So, I am assuming the listeners have some idea of what Lorentz transformations are, but one way to introduce them is to say that we want coordinate transformation such that this this line element is preserved. Let's say rho sigma dx bar or prime rho dx bar sigma. So if we take this as a definition, the property that the speed of light is constant in all frames would just pop out of this definition. Yeah, by the way, x and x prime are just connected to each other via some transformation. X bar are just some functions of x. Right. Okay. This condition can also be written in terms of partial derivatives, such as this. Okay, let me just do it on this side. Sigma over del x mu should be rho mu, eta mu. By the way, this is the Minkowski metric, which is I'm using the signature minus plus plus plus, mostly positive signature. Okay, so if this is my definition and I assume some form of x bar, right, maybe some constants is there, then maybe there is some matrix which I'm calling lambda, and this term is linear in x. So this is some function of x. So imagine that you are expanding a Taylor series or something of that sort. Then there is some other matrix, let's say b mu rho c, let's say, I don't know, rho, or you can do 0 x rho b mu something like that. We have to, let's say, two of these. We should have something like that, and similarly cubic and so on. So in general you can expand it using matrices and certain linear combinations. This term might not be written correctly, but anyway, the point is that if you assume this is the most general form of transformation, going from unbarred coordinates to barred coordinates, and if you put this in this condition that these partial derivatives have to work out in such a way that this multiplying after multiplying by this Minkowski metric, you again get a Minkowski metric. This will put certain constraints on these extra matrices and all. You will basically find that all the higher order terms are 0. Only these two terms survive. So the most general sort of transformation that you can do, which satisfies this basic definition that we started with, would be of the kind this. Some matrix lambda mu nu plus some constant shift a mu. This is called the Lorentz transformation matrix, and also if you just plug this condition back here, you'll be able to find the condition that how this lambda transforms. So it turns out that this is the condition, or in component form you can write it as something like this: lambda mu rho lambda nu sigma equals to eta rho sigma. So in this sense the Minkowski metric is invariant, in the sense that after sandwiching it between the lambda and lambda transpose, but this is the main thing. Okay, and of course it's, or you can find the opposite version as well for the Minkowski metric that has indices on the upstairs. Very similar structure is there. Sigma tau is just mu kappa. Very similar structure. Okay, then yeah. So let's just look at what happens when we have, let's say, two Lorentz transformations in a row. If suppose you have transformed twice, let's call it double bar x mu, that would be some transformation lambda bar mu rho. It will have this sort of structure, but here instead of x we will have a single transformed x rho and some constant a mu, and then I can expand that one as a mu nu rho. This, according to again this definition, would be rho nu x nu plus some other constant a. This bar is just differentiating the two different Lorentz transformations. There is one with lambda and there is one with lambda bar. Similarly, one is constant space-time translation with a, and the second one has the space-time translation with a bar. Okay, so now if we just rearrange stuff, so you can see that the consequence of applying one Lorentz transformation lambda lambda followed by lambda bar is that you get this sort of structure. Or you can also write this thing as lambda a to the or you can write the whole thing together as well if you want, like that. The point is that if you did a transformation lambda followed by lambda bar, then your total transformation looks as though you have transformed with the matrix lambda bar, and your space-time translation vector is not simply a plus a bar, it's actually lambda bar a plus a bar. This is some sort of inhomogeneity in this whole rule. So what we can say is that if a transformation, oh by the way, from the last video we saw that for every symmetry transformation, by the way, yeah, I may have forgotten that these things leave this guy invariant. Dx square minus dt square. This is invariant. Also for a particle that's moving with the speed 1 or c, I have set c to be 1. This is just 0. So therefore in all frames this will be 0, and therefore in all frames dx by dt would be 1. So speed of light would be constant in all frames. Yeah, so the point was, this is a symmetry transformation. Lorentz transformation preserves the speed of light for all inertial frames. The physics is the same, and for every symmetry transformation on Hilbert space there exists a unitary transformation. So since the transformations are labeled by this Lorentz transformation matrix lambda and this space-time translation a, so the corresponding unitary would also be labeled by some lambda and some a, and we found that if we do a transformation lambda followed by another one with lambda bar and a bar, the result is a Lorentz transformation whose this lambda component is just lambda bar lambda, and the space-time translation component is lambda a plus a bar. That's what we found. And we can also just say that the transformation that corresponds to no space-time translation, that is, if all a's are 0, then we get the homogeneous Lorentz group where we have this simpler structure of this type. And similarly, if this lambda is set to identity for all sort of transformation, that is, we are not at all touching boosts or rotations, we are just doing space-time translations, then the structure again simplifies to be of abelian form. U is u of, since this is identity now, so we have a plus a bar. So now this has an abelian structure. for this case. This is pure space-time translations, and this is for a homogeneous subgroup of the Lorentz transformation. And yeah, by the way, any vector in the Hilbert space psi transforms is u lambda a acting on psi. This is just the basic premise, basic definition. Okay. And furthermore, from this property itself, we can also see how the inverse, what's the structure of inverse. So you can quickly see that if you set, for instance, if you want this to be, let's say 1, you would want to set lambda bar to be lambda inverse. And if you want this to be 0, because you want, this is the identity, right? No space-time translation, so this is 0 vector and unit identity matrix in the boost cum rotation sector. So we would want this to be 0. That would mean we will have a bar equal minus lambda bar a, and since lambda bar is lambda inverse, so we can write lambda inverse a. Yeah. So if you were to just follow one Lorentz transformation unitary matrix followed by another one which has this, the Lorentz transformation is lambda inverse and the space-time translation is minus of lambda inverse a, you will eventually by construction find this, and therefore this is just the inverse of this lambda a, since multiplying them is giving us the identity. So therefore inverse of a Lorentz transformation matrix is a Lorentz transformation unitary matrix corresponding to lambda inverse and space-time translation minus lambda inverse a. So we can also figure that out. Okay. And further, more things, for instance, since we know that lambda transpose lambda was eta, and therefore if we take the determinant of this whole equation, we'll find the determinant of lambda square to be 1. This would give us two possibilities. The plus sign is for proper Lorentz transformations and minus 1 is for improper ones. And furthermore, we can also use the component version of this identity, which was written here, this guy. Yeah, so here as well, if we put let's say rho and sigma to be 0 0, you will have eta 0 0, which is minus 1. Similarly here you will have mu this thing, so you will have lambda 0 0 whole square minus and plus lambda, I don't know, 0 I lambda 0, no wait, not this, lambda I 0, yeah, this. So again, we can just shuffle the minus signs, and from there we can see that this lambda 0 0 can either be plus or minus square root 1 plus lambda I 0 lambda I 0. Now since this is a positive number, therefore and this is greater than 1, as you can see, so this means that we can have lambda 0 0 either greater than or equal to 1, or it can be smaller than or equal to minus 1, meaning that if this is a number line 0 1 and minus 1, your lambda 0 0 can be either here or can be either here. It cannot exist in this range. So if we take this sector where lambda 0 0 is positive and greater than 1, then this is called orthogonous group, orthogonous part of this whole thing, and this one is called non-orthogonous. Orthogonous is related to time preserving. So if we have, let's say this can be a small exercise. If let's say you have a time interval delta t which is positive, in a sense that some event happened at A, another event happened in B, and the time interval between them was positive, B occurred after A happened. So if delta t is greater than 0, and if we want to see what happens when we go to another frame by after a Lorentz transformation, So if we want to see whether delta t prime is greater than 0 or does it flip its causality, flip its signs, and becomes negative. So if lambda 0 0 is greater than or equal to 1, we can actually show that for time-like separated events, time-like as in this, if this is time, then this is greater than this. So for time-like separated events, we can show that delta t prime would also be greater than 0. So that's why if this is true, then time-like events are, the causality is preserved. The arrow, it doesn't flip to the negative side. But for space-like events, for time-like events, if the events are separated space is in a space-like interval, then we can have delta t negative. So that corresponds to the idea that space-like separated observers can disagree on the simultaneity of events. Okay, anyway. So yeah, we have 4 things now. We have this guy lambda 0 0, which can be greater than 1 or it can be smaller than 1, and we have determinant of the whole matrix, which can be +1, or this guy can also be -1. And then this is called proper orthochronous subgroup, and usually we deal with this only. Then this one is simply improper orthochronous. This one would be proper non-orthochronous, and so on, improper and non-orthochronous. And to see, so there are other subgroups as well. So this one forms a group, and why we have to show how it forms a group, because if let's say you have 2 Lorentz transformations, lambda and lambda bar once again, and lambda 0 0 corresponding to lambda, the lambda 0 0 corresponding to the first transformation is greater than equal to 1, and the one corresponding to the second one is also that, then we have to show that because we knew that the composite one is lambda bar lambda, we have to show that the 0 0 component of this is also greater than or equal to 1, which can be done. And this I will do a bit quickly, because this sort of derails from the usual flow of the story. So I will just show the calculation quickly. You can pause and ponder over the middle steps. I've done everything already. So yeah, here's the point. So you can see, given we are given this, that first transformation, for first transformation it is orthochronous, the second one it's also orthochronous, and we found that lambda 0 0 square was 1 plus this thing. We found this just a little bit ago. So we can say that this lambda I0 is this, and you can think of this lambda I, you can think of this as a vector, as in you can think of lambda 1 0, lambda 2 0, lambda 3 0, this triplet as a vector. So this lambda I 0 would be the length of this lambda 0, so-called lambda 0 vector. It's a triplet, it's a triplet of numbers. Similarly, you can imagine a lambda 0 with a 0 on top, this vector, as a combination of lambda 0 1, lambda 0 2, lambda 0 3, and so on. Similarly, lambda 0 I would be the dot product or the length squared of that vector. Any case, both of these cases would satisfy this condition, that lambda square is 1 plus lambda 0 I, because that was the original one, and even the second one in which i's are on top. So these are just the reflected components of the lambda matrix, as in if this is your lambda matrix, then some of these are from this column, the other ones are from this column. Yeah. Anyway, so what we basically are saying is that the length of this triplet, this vector, is just lambda 0 0 square minus 1. Similarly for the other one. And so if our first guy had this lambda 0 0 greater than or equal to 1, the second one had lambda bar 0 0 greater than or equal to 1. So if we were to find, by the way, if all this sounds confusing, it's supposed to be confusing because I'm going over it rather quickly. But yeah, we want this guy. So this would be lambda 0 mu lambda mu 0, and upon expanding that, we'll have lambda 0 0, lambda 0 0. This is barred one, this is unbarred one, and then the with the I summed over the 1 2 3 components, I is 0. And since we know that this is sort of a dot product between two different vectors, this one would be the this sort of component, this triplet from the lambda matrix, lambda bar matrix, and this would be this triplet from the lambda matrix, and we are dotting these two vectors. So the point is that this whole thing would have this would have a structure of some length of this vector times length of this vector times some cosine of some sort of angle between them. So, and the length of these vectors can be found as we saw above. It's just the 0 0 components squared minus 1 to the square root. So we can say that the whole thing, this whole thing is just square root of this square minus 1 times square root of unbarred lambda 0 0 square minus 1 times cosine of theta. And the point of this whole thing was that this thing can be at max equal to this product of two square roots. So we can call this a d or delta if we wish. And then from this bound we can easily show that lambda bar lambda 0 0 would be greater than or equal to 1 from this bound. If you just think about how this can reach a maximum and a minimum, then you can put a bound that lambda bar 0 0 would be greater than a certain difference between these two. And exactly speaking, yeah, this guy, you can show that lambda 0 0 would be greater than or equal to this certain difference, because the whole thing is bounded. And then if you can show that this is greater than or equal to 1, this whole thing, then you will indirectly show that this is greater than or equal to 1. Therefore showing that if first transformation was orthogonal, the second transformation was orthogonal, then the composite transformation will also be orthogonal. And this can also be shown. For that, what you can do is start with this fact. There should be zeros and zeros here, but since they just carry along for the right, they come along for the right, so I have omitted them. So you can start with this fact that lambda minus lambda bar squared would always be a positive number, and then just open the square roots, shuffle things around like this, and you will be able to show that this thing is greater than or equal to 1. Again, this was very quick, must have been very confusing, but everything is there on the screen, so yeah, you can figure it out if you want to. But yeah, if you want to skip, you can do that as well. So the point was that the group is the proper Lorentz, the proper orthogonal Lorentz group with +1 determinant and this time preserving property. This forms a subgroup of the Poincare group, which was the one with Lorentz transformation plus space-time translations. And this, if you look at the other ones, for instance, if you try to combine the improper one with it, the improper one in itself does not constitute a subgroup, because first of all it doesn't have an identity. A group has to have an identity. Secondly, if you do two transformations, or let's say two rotations in the improper sector, they will throw you back in the proper sector. So if you just consider the improper one, then the multiplication of two group elements would not be in the sector itself, so it will not be a group. But if you want to combine them, then I think you can form a group by their combination, and they are actually they can be traversed back and forth using a parity translation. Like if you define a matrix P as 1 minus 1 minus 1 minus 1, this inverts the space-time parity, and using this and combining these two, union of these two groups, that would form one group. Similarly, you can do add other subgroups to proper orthogonals, but any subgroup you make of this whole O13 group, any subgroup you want to make, it has to have this proper orthogonal group inside. That's because it has an identity inside it. Right. Okay. So briefly speaking, what I have covered is that Lorentz transformations preserve this line element, they preserve the light speed. This is the most general sort of transformation possible in case of which respects this line element preservation. And from this many things can come out. This property comes out from here. Other than that, if we go back to the Hilbert space picture, doing a physical transformation, a physical symmetry transformation on the system would correspond to doing a unitary transformation, a linear unitary transformation on the Hilbert space, which follows this composition rule. And from there you can figure out what is the inverse. From there you can see that the space-time translations are abelian. They form a abelian group. Meanwhile the homogeneous sector is this form, which we usually deal with in typical relativity situations. And then I talked about what is an orthochronous group, which preserves the time-like direction for the time-like separated events. And there are many unions you can make from the whole O1, 3. This one belongs to SO1, 3, and in particular SO plus, I think. Plus denotes this one. Yeah, for this one we have to do something. Maybe you can put an arrow or something denoting this greater than or equal to 1. Okay, if we go to Poincare algebra, now what we can do is think about the Lorentz transformation around the identity, just like we did in the previous session, because as we saw that most of the information is present around the identity, so we can expand lambda as identity plus some matrix which we are calling omega. If we want to write it in this form, component form, we can write it as del mu nu plus omega mu nu. And then again, just from this definition, lambda and theta lambda should be lambda itself. If you apply it in component form, you will be able to see that omega mu nu has to be negative of omega nu mu, or using the Minkowski metric to lower the indices, we can show that omega mu nu is negative omega nu mu, or we can say that this is the antisymmetric matrix, and since it's the mu runs over 4 labels 0, 1, 2, 3, a 4 by 4 antisymmetric matrix would have 4 times 4 minus 1 by 2, that is 4 times 3 by 2, which is 6 independent parameters. So this group is parameterized by 6 independent parameters, which are the 3 rotations and 3 boosts, but we can talk about it later. And furthermore, the space-time translation part, we can say that this a mu is also a little translation in space and time, parameterized by epsilon mu. These are 4 extra parameters, so a total of 10 parameters are present in the Lorentz group, not the Lorentz group, the Poincare group. But yeah, we can take this one, and then we can say that this is the Lorentz transformation that we are doing on the physical system. Then if you talk about the unitary transformation that corresponds to transformations on the Hilbert space, those will be they were of this form. Now infinitesimally around identity, they would be of the form 1 plus, since we can pull out one I to make this part Hermitian. So around identity we will have this guy, this matrix omega mu nu, and some generators. We can call them J mu nu. Some people also call them M mu nu. And similarly, the generator this for this part epsilon mu rho, and 4 generators for the this sector, the space-time translation sector. And and there will be other terms. I'm just keeping things linear in these omega and epsilon, and of course this just goes back to the original things in certain limits. For example, if epsilon are all 0, then we will just have 1 plus omega or something like that. and if these are 0, then we will have 1 minus I epsilon p. This is just because we know that lambda 1 0 is identity, and u1a forms abelian structures, and similarly as we saw that around identity the whole thing has this omega sitting around. Therefore this so we posit that these are the generators in the unitary version of the Lorentz transformation. Now we can try to find the structure of these generators. This can be done as follows. Well, by the way, since I have pulled out i's outside, so these are obviously Hermitian j. If so, I'll write j, but it means this j mu nu. This is a matrix. Since this is a generator, j mu nu is a matrix. Not only it is one matrix, since mu and nu are indices, these are actually 6 matrices. And similarly, p are also 4 matrices. These are 4 different matrices, and these mu nu are the space-time indices. So they do not interfere with these. So from the space-time perspective, omega and j are just numbers for them. Like you can write omega dot j as j dot omega, even though these are matrices, but these are matrices not in the space-time perspective. What that means is that if you, let's say, get some certain matrix omega 0 1 and similarly omega 0 j 0 1 here, this j 0 1, they act on the states of the Hilbert space. From the space-time perspective, these are just constants, so you can like shuffle them around in the mu nu sector, but not in the Hilbert space sector. For example, if you had j mu nu and j rho sigma, two j's were present, you cannot write j rho sigma and j mu nu, because these are different matrices that act on the Hilbert space states. Well, anyway, what I was saying was that j dagger is j, because this is Hermitian, and similarly this is also Hermitian. P dagger is p. What I mean by this statement is that j mu nu dagger is j, because j is a stand in for 6 different matrices labeled by mu and nu. You can forget about even space-time. You can just think that there are 6 matrices and they are labeled by mu and nu. You can just think like that. You don't have to picture mu and nu being space-time indices or being Lorentz or anything like that. From the Hilbert space perspective, what I mean is that these you have to imagine that these some things, this u is acting on the states on the hill that are present in the Hilbert space. Okay, first thing was that these are Hermitian. Second is that since this is antisymmetric in mu and nu, okay, mu and nu are just labels. These are space-time labels. They are irrelevant from the perspective of Hilbert space, but still mu and nu, this is antisymmetric in mu and nu. That would mean that j mu nu will also be antisymmetric in mu and nu. And then we can look at how things change in the Hilbert space. So in particular, we can look at how, wait, just give me 1 second. Yeah, in particular, we can look at how this u itself changes under Lorentz transformations, as in unitary transformation that are representations of Lorentz group. So what we want is to sandwich an operator, the operator u, corresponding to some Lorentz transformation between u and u inverse that correspond to some other Lorentz transformation. Let's call these ones lambda, and they are parameterized by lambda and a. And these ones are, let's say, these are infinitesimals, as in lambda is just 1 plus omega and a is just epsilon, just in this spirit that we did here, just like that. This in the structure of infinitesimal Lorentz transformation was this. Okay, so we can look at this guy, and since we found earlier that the inverse of any lambda a is just non-inverted U matrix, but with lambda inverse and space-time translation lambda inverse acting on A. From this information, we can resolve this whole thing. Also, we saw that U of lambda A, I mean lambda bar A bar followed by some lambda and A was just U of lambda bar lambda and lambda bar A plus A bar. So from these two things, we can try to simplify this, and it simplifies a lot. It just becomes, this whole thing just becomes U of, so the Lorentz transformation part is just 1 plus lambda omega lambda inverse. That's what becomes in this part, because at the end of this whole thing is just another unitary transformation corresponding to some Lorentz Lorentz matrix and some space-time translation vector, and the space-time translation vector comes out to be of this form. Okay, now since these two things are equal, we can expand this guy using this definition that we had, and we can do the similar thing on the right hand side, and we just have to keep track of all the indices. I will show you the computation. The computation is an important part, but it's also the boring part, so I will show that to you and you can follow it along. You can try to reproduce it and look at it if you get stuck. Yeah, so where is it? Okay, yeah, here's what, here I think, yeah, okay. Yeah, you can see that here I'm doing exactly the same thing, first combining these and replacing the inverse with that rule that we found, and then combining these two into one, and then followed by some algebra leading to this condition that I just wrote down earlier. And then I substituted in place of this infinitesimal unitary transformation the form of the generators. Omega dot j and epsilon dot p are the space-time dot products, 4 dot products. And then there are additional terms. We will just ignore all the higher order terms if it's an order omega squared term or an order epsilon squared term, or terms which have epsilon and omega. Both of these, we'll ignore all of these. We are working around identity, infinitesimally small. So and on the right hand side as well, I have to manipulate all the objects. So you can see the calculations by pausing if you want to reproduce them. Sometimes I use Minkowski metric to lower and raise indices. Also I use this property a lot, that lambda inverse mu nu is lambda nu mu. This can also be proved easily using the basic properties. And most of the things cancel out and we get this beautiful result. So the thing that was noticing is that the way this equation is telling us the way J transforms under U and U inverse. So you can imagine J as some matrix, and we are asking how this matrix that acts on the Hilbert space transforms when we do some Lorentz transformation lambda. It tells us how it does that. It tells us there is this 2 factors of lambda, there is J, and there are 2 factors of space-time translation A. In particular, if let's say there is no space-time translation, you are just looking at pure Lorentz homogeneous transformations, then this would go to 0. You will just have this thing, and this is just how tensors transform. So J would be just a Lorentz tensor, because that's how tensors transform. For each label on the tensor, there is 1 lambda. And similarly for the p mu, this is the rule that the way 4 space-time translation generators transform under U or under Lorentz transformations is just like a 4 vector p again. You can also look at pure translations if you want, as in you just let A be A and let these lambda be identity, as in Kronecker mu nu, and that will give you that J transforms like that. It is still a little complicated, not a very good looking thing, but you can see the other one, the simpler one, does not transform at all under pure translations. That means that does tell us that P mu is indeed the generator of space-time translations. Okay, for the next part, what we will do is again we will use this property again, this one, but what we found is these two from this and this, the way how J mu transforms in general and the way how P mu transforms in general. Now what we will do is in place of these lambda and a, we will use infinitesimal generators again, as in we will put lambda equals 1 plus omega again. Now this omega is different from the omega that we used for to reach this step, because here as well we use these omegas, and here as well we in the middle guy we use infinitesimal transformation, but we should think of that omega as a different one. We can call it omega bar if you want, but since all the omegas are cancelled in the process, so we can just use this omega label once again, it's fine, but in principle it's a different one. So again, u of 1 plus omega and epsilon, in place of a we'll use epsilon, would again be of the form 1 plus I by 2 omega dot j minus I epsilon dot p. And for both of these you will have to find u inverse, and again u inverse, the rule was that u inverse is just u inverse of lambda a was u of lambda inverse and minus of lambda inverse a. So if this is my u, then u inverse according to this rule would be something like that, and the inverse of 1 plus omega matrix would be 1 over 1 plus omega matrix, which would roughly be 1 minus omega plus higher order terms in omega. So inverse of 1 plus omega matrix would be 1 minus omega. Omega is a matrix, by the way, and this is also a matrix. So that's how we can find the inverse, and we can put all these quantities in inverses and the normal ones. We can expand the right hand side and so on. We should be careful with the indices, and eventually we will find that the j mu's, our goal is to remove omegas and epsilons from the picture, so we will match the indices. If they are summed over, we can change their names and so on, but the final goal is to remove omegas and epsilons from both sides of the equation. And after doing that, we left with the commutators of j's and commutators of p with j's, which have this form. The way I remember is just that if you just remember the first term, there is just one j, and you remember the structure of mu nu rho sigma here, and then subtract. First you have to subtract mu, same thing but with mu and nu replace, and then you have to subtract this whole copy of this whole bracket but with rho and sigma replaced, so you just get back this 4 terms. It is the famous Lorentz transformation commutators. I mean, that's how the generators commute, and the same thing can be found for the commutators with p from the same procedure. And of course the generators of p among themselves is 0, because they commute, they are space-time translation, they form an abelian group, so they commute. And here's a picture. You can imagine j mu nu as since these were antisymmetric, you can imagine a matrix of matrices with 0 1 0 2 and so on, and this half is just a minus reflection of the top ones. We define these top ones as k1 k2 k3, 3 boost generators, and we define these as j1 j3 minus j2 j1, just like this. They're like j1 is just j12 something like sorry, j not j12, j23. Similarly j2 is j31, and similarly j3 is j12. With these definitions, we will be able to see that the commutator relation of j's is just the commutation of angular momentum algebra, and all the other Poincare algebra commutators drop out. By the way, we also let p three p's because there were four p's, right? P1, P2, P3, and P0. This one we will call H, and these are our pi, the momentum generators, and H is the generator of time translations. It's also called Hamiltonian, and all the generators follow through. So what we have done in a sense is just that what we have done is that we looked at how a certain matrix, some matrix, how a certain matrix M changes under a Lorentz transformation on the Hilbert space. So this is how it changes. Now first we replaced M with a Lorentz transformation matrix itself of infinitesimal form, like this. From this we found how the generators transform under Lorentz transformation, how J mu nu transforms and how does P mu transform. And then we replace these ones with the infinitesimal version itself in order to find how the J's and the P's commute with one another. That's how we did it. So that's how we found the algebra of the Poincare group. Yeah, finally, since we now know that P mu generate the abelian sector of the group, so we can just write u1 and some vector a, some vector 4 vector a mu. Since we know its generators are were minus I epsilon rho P mu of this form in infinitesimal form. We can see, since last time we saw that abelian ones have the structure of exponential e to the power I times the generators, which are minus P mu. So we can write it as this a mu P mu. The pure translations, the unitary transformations corresponding to pure translations in the physical state on the Hilbert side. This is the operator.